Good evening. Okay, we are entering the eighth week of the lessons. So I'll share my screen, then we will see few questions and we'll try to solve it together. Okay, so without wasting much time, I'll share the screen now. So this is week 8th of the course Water and Wastewater Treatment Problem Solving Session. I am Mansi Tripathi, Research Scholar at IIT Madras. I am conducting these sessions so that we can help you solve the problems in the assignments as well as in the examination. So we'll move forward and see the question. So here in this time most of the questions will be numerical based, so try to solve them and then you can match the answer. Consider a water treatment plant having Q in, means a water treatment plant getting the influent discharge as 12960 meter cube per day. We have the dynamic viscosity of water, dynamic viscosity. Okay, this is there difference between kinematic viscosity and the dynamic viscosity. We should be well aware of that. I hope you know the difference. Okay, the velocity gradient of the rapid mixing tank is this G is given. The tank is used to blend 35 milligram per liter of alum with the flow. The incoming flow is this, and for the detention period of 2 minutes. So the input power required for mixing is, we know the formula of power. It is related, like I'm not writing the whole formula, but it is related with G and the mu, and of course the volume. So I am writing here proportionality constant. So just to show you how it is related, I am not writing the powers as well as the volume value, so that you can use your own notes to solve this problem. I am just writing how this formula will be given, and this P we will get in watts. Here the question is in kilowatt, so be mindful of that. So I'll give you a minute to solve the problem, then we will see the answer. Okay, we will see the solution. So the power input in watt. Question was in kilowatt, okay, but here it's in watt. Watt required for rapid mixing is given by this expression. Okay, so this square term was missing in the previous thing. That's why I have written proportionality constant instead of the this equal to. So mu is the dynamic viscosity. If I say kinematic viscosity is this, which is mu divided by the density. So this is how kinematic viscosity is written, but here dynamic viscosity is required. We have mu value. This mu value is the typical value for water. Okay, so wherever if we say water is there and mu value is not given, then you should just take it as this, 10 raised to power minus 3 Newton second per meter square, because this is the typical value of the water, typical mu value of the water. So if in question just water is given, you have to assume the kinematic viscosity. G is 850 per second. So volume we can calculate from this time versus q. What is velocity? Volume is equal to discharge into time. So using the same formula we have calculated it. So first of all we are calculating discharge in meter cube per second, then we are multiplying it with the time. 2 minutes is equal to 120 seconds, and here we have calculated day into meter cube per second, then we have kept that in formula and calculated everything. Okay, so this is how this is not 8250, this will be square. 8250 square into 10 raised to power 10 raised to power minus 3, that is mu value, and this is volume in meter cube. This is what we have getting in watts. We have to convert it into kilowatt because the question has asked us to answer in kilowatts. We have to be very mindful of that. Otherwise, if even if you are doing it correctly, the computer will read it wrong. So which is 13.005 kilowatt. Also, in the questions, this will be the scenario, like the computer will accept the response from 12.5 to 13.5. So small error will be fine. Okay, so there is no issue. You can directly do it. Coming towards next question. A water treatment plant has a flow rate of 504 meter cube per hour. This is Q. A particle of certain size, a particle of certain size has settling velocity of 0.14 centimeter per second, and we need to find out the required plan area, okay, of type 1 settling to remove 90% of the particle of this size. We need to calculate the plan area. We have the q value, we have the settling velocity, we need to find out the area. Generally this plan area we have to calculate. If we just want to calculate for the type 1 settling, means the particle is discrete. Type 1 settling means discrete. So Stokes law will be valid here. So you can use the Stokes law to solve this question. Okay. So please try to solve this question, then we will see the solution in few minutes. We'll see the solution now. So we have Q is equal to 504 meter cube per hour. We need to take care of the unit, so we are changing all the information in a uniform unit. So we have converted it to 0.48 meter cube per second. Just divided it by 3600. We will get this. Vs is 0.14 centimeter per second, which is 0.004 meter per second. So plan area required will be very simple. We have Q, we have Vs. So because this is a discrete particle, so there will be no role of flocculation and all. So we can directly divide Q by Vs. So this is we got what we got. But we want to remove the 90% of the particle. So we can reduce the plan area because we know there will be, if the area is more, efficiency will be more. So this is with when we want 100% efficiency, that too in ideal condition, means when the particle is discrete, okay, then only this thing will work. But to remove 90%, we can reduce the plan area by 10%. So just multiply 100 by 0.9, we get 90 meters square. So this is your answer. Next question will be the connection of two questions. So please note down the information. So this is the common data for the question number 3 and 4 which are coming. We have to consider an ideal horizontal settling basin. Okay, ideal horizontal settling basin. It is having depth of 3 meter. Q in is going is 9600 meter cube per day. We have the settling time T at temperature of 20 degrees Celsius. As I have told you, mu will always be this in case of 20 degrees Celsius for water. So mu is 10 raised to power minus 3 kg per meter square, and rho is this 1000 kg per meter cube. We have to assume the laminar flow condition. So first note down this information, then I can show you the questions. Okay, we'll see to the move towards the question. The surface overflow rate in the settling tank is, okay, surface overflow rate means if you see the unit, it's in the terms of velocity. So velocity can be calculated in various ways. So please try to answer this question. We have seen the information that was given in the previous slide. Using that information, we have to calculate the surface overflow rate in the settling tank. So this is the solution to the previous problem. Settling basin detention time is 7.5 hours. We have converted it into seconds by multiplying it with 3600. The flow over rate we can calculate very easily by depth divided by the settling time. We have, for the horizontal flow, we have the Q coming. Okay, we have the depth. So we need to calculate the surface overflow rate, velocity, Vs. It can be calculated by the depth and the time to travel this depth, because we have been given settling time. So this is what we got. Okay, so this is your answer, 9.6 meter cube per meter square per day. Moving towards next question. Consider a spherical sand particle having diameter this and specific gravity of 2.65. The percentage removal of such sand particle in the settling tank is, we need to find out using the Stokes law, we need to find out the velocity of this particle, then we can find out the efficiency of the particle. So you have all the values, we have kinematic viscosity, we have GS values. Okay, we know the formula, V is equal to G by 18 GS minus 1 dp square upon nu. So here I have written nu. What is nu? Is equal to mu by rho. So putting these information, we can calculate the velocity, settling velocity of this particular particle and the settling velocity that we have already provided. So we can find out the efficiency using those things. So please try to solve this question, then we will see the solution. You can match it with yours. We will see the solution now. So as I have already told, this will be the calculation. Okay. So here in place of mu by rho has been already kept. We know the d. This is not an empirical formula. So all the units should be same. D 0.01 mm should be written in form of meters. G 9.18. Capital G, which I am referring to as GS, is 2.65. Rho we know, mu we know. So when we'll keep all these things, we will get this value. So the removal efficiency will be whatever it wants and what we have given. Okay, required versus provided. Required. So this is required and what is provided into 100. So this is what we get. 76.5% of this particle, of the particle size 0.01 mm will be removed. Okay, rest of the particle will remain inside the water body. We'll move towards next question. So now numerical questions are finished. Few questions, one more I think question is there. Most of the questions are not theoretical, so we will do it fast. Select the correct statement regarding the flocculation. So tapered flocculation means the value of G is decreasing, is more efficient when compared to conventional flocculation. Okay. Here we are talking about the flocculation is the process that promotes aggregation of small particle into larger aggregate to enhance their removal by gravity. The macroscale mechanism of flocculation is caused by Brownian motion. Okay, the macroscale and Brownian motion. Be mindful what it is talking. The microscale mechanism of flocculation is caused by relative motion of fluids. The typical design value of velocity gradient are in the range of 20 to 80 per second. So please answer this question, then we will see the answers. Then you can match yours. We will see the answers now. So A, B and E are correct. And here in this case, if these things are reversed, then it will become correct. Okay, microscale is caused by Brownian motion and macro by relative motion of fluid. Okay, rest of the things are correct. We'll move towards next question. Match the process with their primary design variables. Rapid mix design, flocculation design and type 1 settling. So these are their primary design variables. Please match the values, then we will see the answers. We'll see the solutions now. So the option D is correct, which says rapid mix design is done by mixing intensity, means G values. Okay, and the rapid mixing should be very fast, means this very high G values should be given for short duration. B is going to 1. No, this I think it's wrong. This rapid mix design is with detention time and mean velocity gradient. Okay, and this critical settling velocity is settling tank, it's very correct. And C is going with 2. Flocculation design is with mixing intensity. So here G values will be given, but for very long time, and G will be very less, 20 to 80 per second, and for rapid it's around 100 to 300. So that is the change here. We'll move towards next question. Which one of the following type of settling phenomena can be analyzed by the sedimentation law of Newton and Stokes? Both the laws are applying, Stokes law as well as Newton law. So which of these phenomena can be realized with that? We'll see the solution. So this is discrete settling. Stokes law, it's about discrete particles. Okay, and Newton's law is related to mu values. Means it's related to macro scale. We'll move towards next question. A surface water flow, this is a numerical question, 15,000 meter cube per day is coagulated by adding 50 milligram per liter of ferrous sulfate and an equivalent dose of lime. If the lime is 87% pure, then the quantity of lime required is, we are adding ferrous sulfate. This consumes alkalinity, means lime. So we are adding some lime to maintain that alkalinity because it consumes it. So we need to know the equation and all these things. So please, it's already mentioned it is consuming an equivalent dose of lime. So we equivalent uh, equivalent weight of one thing is equal to equivalent weight of another thing. So using that theory, you can find out how much lime is consumed when 50 milligram per liter of ferrous sulfate is consumed. Try to find out answer of this question. We'll see answers in few minutes. We'll see the solution now. So one equivalent of ferrous sulfate is, we know the molecular weight of ferrous sulfate, that is 278, and we know the molecular weight of CaO, which is 56. So one equivalent of ferrous sulfate is, because one it is saying equivalent dose of lime. It is equal to equivalent dose of lime. So both the equivalent weight should be same. So one equivalent weight of ferrous sulfate is 278 by 2. This is n value, means when it reacts these number of electron it exchanges, and same goes for lime. So 28. One equivalent of ferrous sulfate reacts with one equivalent dose of lime. So means 139 gram of ferrous sulfate requires 28 gram of lime. 1 gram of ferrous sulfate requires 28 divided by 139 gram of lime. So how much 50 milligram will it require? So this is the solution. Okay, this is per liter, but we know the Q in values, how much it is coming, 15 mld. So just putting all these values together, so we will get the values in kilogram per day. But the lime is just 87% pure, so we will need some extra, because this is lime required when it is 100% pure. So divided by 0.87 to account this impurity, we will get this thing. So this is our answer. We'll move towards next question. What are the concentration of aluminum and sulfate in 3 molar aluminum sulfate solution? Okay, 3 molar aluminum sulfate is there. Al2SO4. This is 3 molar. So what is the concentration of aluminum and sulfate? So what, when it will dissociate, what all things will be formed? Please try to answer this question. We'll see the solution. So this is the solution, but how it is coming? Like this. 3 mole Al2SO4 thrice per liter. So the relative concentration we have to calculate. So this is how these things are calculated. We have 3 molar of Al2SO4 thrice. So when it will dissociate, it will give 2 moles of Al3 plus. Like it's like this. Okay. So this 2 is coming here. So it came around 6 mole of Al3 plus. And when this same 3 mole of Al2, this dissociated, it gave 3 moles of sulfate. So this came as 9. So 6 is to 9 molar of aluminum and sulfate. So this is nothing but the coefficient values. Okay, so these coefficient values 2 and 3. We'll move towards next question. Consider a coagulation treatment plant. We know the flow, we'll know the alum dosing. Influent suspended solid concentration we know. Effluent suspended solid concentration we know. Because of alum dosing, something has been coagulated. Okay. Then stoichiometric equation of alum, Al2SO4 thrice dot 14H2O yields to 2AlOH3 H plus ions, means acidic condition because it is consuming alkalinity, sulfate and H2O. The total amount of dry sludge solid produced per day will be, we know the influent, we know the effluent. So whatever remaining will go inside sludge. So 32 minus 17 milligram per liter is going as sludge. So we have to calculate the same in kg per day. Okay, try to find out the answer of this question. We will see the solution in few minutes. We'll see the solution now. So we know the flow, which is 27,000 meter cube per day. Alum added is 25 milligram per day. From the equation, we can see that 1 mole of alum produces 2 mole of Al2OH thrice. 1 mole of alum is producing 2 mole of Al2OH thrice. So molecular weight of alum we know of AlOH thrice. Aluminum hydroxide we call it. Then 594 gram of alum produces 2 into 78 gram of aluminum hydroxide to precipitate at solid sludge. So 1 gram of aluminum will produce 2 into 78 by 594. This much gram of aluminum hydroxide. So 20 milligram per liter produce this much. And suspended solids removed 15 milligram per liter. So how much total is removed? This is from the suspended solid and this is from the aluminum's own sludge. So these are the total which needs to be removed. Also, looking at these units, I would like to tell milligram per liter is equal to gram per meter cube, which is equal to ppm, that is parts per million. So milligram per liter, milligram when we want to write as gram, we write as that 10 raised to power minus 3, and liter when we want to write as meter cube, we write 10 raised to power minus 3. So that is how gram per meter cube. So here that's why there is this direct change. Okay, this thing will be same actually. It's wrongly written like this. So total dry sludge removed is when we multiply it by 27,000. This is what we will get. I'll check this calculation. So this is wrong. This is correct one. Okay, 21.575 gram per meter cube. So when we multiply it by the flow that we are receiving, we will get this. So this is your answer. So solution is indicated here, and this is the range of values in which solution is accepted by the computer. So this is the last question. A flocculation chamber is equipped with 100-meter long, 0.32 meter wide paddles. Both paddles are supported parallel to horizontal shaft. And horizontal shaft is there. We know the paddles are there. We know the wideness 0.32, and we know how long they are. And both are are supported by the horizontal shaft. The shaft rotation speed is 3.5 rpm. Center line of the paddle from the shaft is 1.7.5 meter. We know this coefficient of drag. The ratio of velocity of paddle with respect to water to velocity of paddle with respect to fixed coordinate. We know this value of k also. The power consumption. So this is what we know. The power consumption by the shaft is. So here we have to calculate the power. The formula will be using the Newton's form, like half rho v square, something like that, CD. The formula I don't remember correctly, but it will be something like that. So you can check the formula from the notes and you can solve the question. Please try to solve this question. Then we will see the solution in few minutes. Okay, we'll see the solution now. So the power is given by half CD rho W. AP means the area of paddles. VPQ means velocity of paddles Q. So Vp can be calculated by the RPM values K into 2 pi Rn. R is the radius. So K we have 0.75. Okay. 2 into 3.14 into 1.75. 1.75 means the center line of the paddle from the shaft. So this is the radius they're talking about. Into 35 by 60, because that was in RPM, means rotations per minute. We have to convert them into 60. So this is the area of the paddles. Actually, this diagram will be something like this. This is the paddle. Two paddles will be there. This is 10 meters. This will be 1.75 meters and width is 0.32. Okay. So this is the thing given here. We have calculated the AP and then the power. So this was the last question. That's all for today. Okay, I'll show question number 8. So this is the question number 8. You want to see the solution or just the question? Okay. So here it is, the question is asking equivalent dose of lime, means both the equivalent dose will be same. So that is the main thing that we have to do in this question. So that is why we have equated this thing. If you can make out this, then the question is very easy to solve. You can check the solution and you can see if there is any doubt. Okay, then we will close the session now. In case of any doubt, you can like there is a platform in the NPTEL. You can write your questions there, or you can ask in the next session. We'll close for today now. Thank you so much.